Hello. Hi. Okay. Hello, everyone. Hello. Who all are there? Can you please drop some message in the comment box? Okay. Hello, everyone. Hello. Hi, Siddhant. Are you there? Okay. Uh, Hello. Yeah. Who all are there? Tell me the name quickly. Amog. Amog, are you there? Samuel. Naman. Siddhant. Siddhant Shirke. Okay. And Ramcharan Kondania. Okay. Kondania is not there. Okay. Okay. Anyways. What about Siddhant Kormangla? Siddhant. Okay. And Aditya. Uh, yeah. So Aditya, Naman, Amog, and Ramcharan and Siddhant Shirke, right? Okay. 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 Fine. So we are getting late. Okay. So what we have done last class? Can you tell me? Like what is the last portion we have covered last class? First order we have done, right? Ramcharan, we have done first order, right? Siddhant, you were there in the last class. Hello. Okay, fine. So, like basically, first order we have done. Okay, and in the first order, we'll see some questions onto this. Okay, which is important, and that we call it as pressure-related problems. Okay, in first order only, we'll finish this. It's not a question; it's a concept, basically. Okay, because most of the questions you'll get, which is related to pressure, also, right? So, write down next the heading. You write down, all of you, pressure-related problem, that you write down first, pressure related problem. Yeah, hello. Sorry, it's not shared. I think it's shared. Acha, just a minute, just a minute, let me check once. Oh yeah, I have shared over there. Anyways, huh? So okay, now it's fine. Okay, okay. So you write down the heading over there, that is pressure related problem. Okay, just a second, we'll start. Okay, how many of you are there in YouTube live? Only you are there, no? I can. Okay. Okay, so next we are going to see in this, that is pressure related problem. Okay, how do we see the question in which pressures are given? Right, just one concept you have to keep in mind. Okay, and what is that concept? That we know pressure and concentration are directly proportional. Right, pressure and concentration are directly proportional. Okay, so you see, and we are discussing about first order questions only into this. Okay, now suppose if I write down this reaction, A gas gives B, suppose 2B, if I write down 2B gas and C gas here. Suppose this is a reaction we have. Okay, so in this reaction, since we are talking about pressure, so all reactant and product are must be in gaseous state, right? Must be in gaseous state. Can you tell me the expression for the rate constant and temperature for first law? What it is? K is equals to 1 by T ln A naught by AT. Is it there? Yeah, A naught minus X is AT only, right? This is the expression that we have done in the last class for first order reaction. Okay, and since we know that this pressure and concentration is directly proportional, right? Pressure and concentration directly proportional. So instead of this initial concentration, we can write what? Initial pressure also, P naught. And instead of this final concentration, we can write final pressure, PT also. Yes, Siddhant. Siddhant, you were there in the last class? No, okay, okay. Just you do one thing. This is the formula for first order reaction. Okay. K is the rate constant, T is the time, A naught is the initial concentration, and AT is the final concentration. Means final concentration means concentration at the point of time T. Correct? So basically A naught is the concentration at T is equals to 0, and AT is the concentration at T is equals to T. Correct? Now, on the basis of this reaction only, this expression only, we are going to represent this. Okay. Now, suppose if I assume at t is equals to 0, initial time, right? At t0, the initial pressure is P naught, and there is no B and C present over here. Correct? We are assuming this, right? Now, at time t is equals to T, right? A starts converting into B and C. So in this, during this time, what happens? Some of the pressure of A will decrease. Suppose P naught minus P1 if I write, right? And correspondingly, what is the pressure of B we get here? It is 2P1, because the coefficient is 2. 1 gives 2, so P1 gives 2P1. 1 gives 1, so P1 gives what? P1 here. So this will be the pressure at time T. right? If I ask you what is the total initial pressure, total initial pressure, initial pressure is P naught, right? Because there is only A, there's no B and C. So total initial pressure means what? You have to add all these pressure term, right? Since there is no B and C, so total initial pressure is P naught only. What is the pressure, total pressure at time T? Total pressure at time T, right? So since when the proceeds, so some of the A converts into B and C like at the same time, right? So we have pressure of A also, whatever the value, that is another thing. But we have some pressure of A also, some pressure of B also, and C also. So we have to add all this pressure term, correct, at time T. So P naught minus P1 plus 2P1 plus P1. Is it clear, all of you? And we get what? P naught plus 2P1. Okay. This is the total pressure at time t. Now, if I write here at time t is equals to infinity, means at very long time, after a very long time, what we assume that this A has been converted into B and C completely, right? So, like this, if it is given at infinite time, the pressure of A becomes zero, because what we are assuming, A converts into B and C. There is no more A present into the reaction vessel. Is it clear? Okay, so all these A converted into B. So here we get what? 2 P naught, right? P naught gives 2 P naught, and this P naught gives what? P naught here. So total pressure at infinite time, right? At infinite time, the total pressure is what? 2 P naught plus P naught. A is 0. So we'll write what? 3 P naught. Is it clear? Now this is what you have to calculate, right? Now, you see, depending on this stoichiometric coefficient, 1, 2, and 1 we are taking over here, right? So, depending on this stoichiometric coefficient, the expression of this pressure will change, yes or no, right? Because of 2 only we get 2P1. If it is 3, we'll get 3P1 over here. Everything will change. So, we are not sure, or we cannot say that what reaction you will get in the exam. So you don't have to memorize this. You have to understand this, that how do we write down the pressure term for each reactant and product. Is it clear? Right? So now you see, if I ask you at time t, the total pressure is P naught plus 2P1, right? What is the partial pressure of B? 2P1. What is the partial pressure of C? P1. What is the partial pressure of A? P naught minus P1, right? This is clear. So this thing they can ask you at any point of time. Okay, so suppose if I have to write down the rate law expression, or the expression for the first order equation, right, in terms of pressure, and that expression would be this: K is equals to, everything will be same, K is equals to 1 divided by time t, ln of initial pressure is what? P naught. And after time t, the pressure is what? Pt. Okay. And if you see, this P naught and Pt is the pressure of reactant, because this term A naught by At is the pressure, is the concentration of what? Reactant only we write. Right? So this is the initial pressure of reactant, and this is the pressure of reactant, not total pressure. Okay, Pt is not the total pressure. You keep this in mind. It is the pressure of reactant at time t. And what is that pressure? Pt is equals to what we have at time t, P naught minus P1. This is what you have to substitute over here. Did you get this, all of you? Yeah, Aditya. Aditya is not there. Aditya and Naman is not there. Why they are not attending these classes? Okay. Okay, anyways. So all these things you have to keep in mind. What is the partial pressure of B, C, A at any point of time? Okay. Now suppose on this thing only, if I write down this in terms of log, that will be what? 2.303 by T log of P naught by P naught minus P1. That is nothing but PT we have. Yes, Ramcharan, is it clear? Siddhant, what about you? Okay. Now you see one question if I give you here. Okay. One question. You have to write down this expression. Okay. But what is given? The pressure according to this reaction only. All this question we are looking at according to this reaction only. The pressure of B, right, PB, after time T, it is given as P2. Did you get this? Pressure is given. Pressure of B after time T is P2. Okay, you have to find out this expression, K and T expression you have to write down. So write down K and T expression in terms of P naught, which is the initial pressure we have, and P2, which is given in this equation. Did you get my question? Write down the expression. What is the expression you got? Yeah, correct. So basically, you see this P2 is given, right? So P2 is nothing but 2P1 according to the question, right? So what we can write, 2P1 is equals to P2. And here in the expression, we have P1 term, which we have to replace in terms of P2. So P1 is equals to what? P2 by 2. We'll get the expression. Correct? So expression will be this. I'll write down the final expression. That will be 1 by T ln. We'll get 2P naught in the numerator divided by 2P naught minus P2. Is it correct? Okay. Now the next one you see. Okay. So let me write down the reaction. So reaction that we are assuming is this only. A gas, the same reaction, 2B gas plus C gas. Okay. And we have also written this thing. This is P naught. This is P naught minus P1 after time T. It is 0. It is 2P1. And it is 0. It is P1. Right? First question we have done. Second question you write down. And the second question we have here, that is the total pressure. See, they can frame any question from here, okay? And I don't have any book, and I'm giving you all this question. There's no any book, okay? I'm just trying to frame the question, okay? The total pressure of product, if I say total pressure of product after time t is P2, then you have to find out the expression of K. So what we'll write here?
P naught plus 2P1 equals to P2.
Yeah. So total pressure of product is what? It is 2P1 of B plus P1 of C is equals to what? P2. So P1 is equals to what? P2 by 3. Replace this P1 as P2 by 3 in the expression. We'll get what? K is equals to 1 by T ln 3P naught divided by 3P naught minus P2. This is the expression we get. Correct? Total pressure after time T. If it is given that total pressure after time T is P2, then what will be the expression?
Then P naught plus 2P1 equals to
What?
Then P naught plus 2P1 equals to P2.
P naught plus 2P1 is equals to P2. Yeah. So we'll write what total pressure after time t. We have already written this thing in the first slide. And that is we have to add these things, right? So P naught plus 2P1 is equals to P2. And we have to replace this P1 in terms of P naught and P2. So we'll get what? P naught minus P2. Sorry, P2 minus P naught, no? We'll write P2 minus P naught divided by 2 is equals to what? P1. So P1 I'll substitute into that expression, and that will be K is equals to 1 by T ln of P naught divided by P naught minus P1, and P1 is what? This thing. P2 minus P1 by 2, and that will be the expression.
Yes.
Correct?
Yes.
P2 minus P naught, here we have, no? This is also P naught. P1 is this, right? Now you just take LCM and you solve this, you'll get the expression. So like this, you'll get many questions. Pressure related problem is very important for JE point of view. Okay, how do we write down the expression of pressure thing into this? If I give you the total pressure of A after time t, suppose the next one, total pressure of A reactant after time t is P2. Can you do this? Quickly tell me the answer. Oh yeah, so it's direct only. So nothing you have to do into this. Okay, so P naught minus P1 is P2 only, right? So P1 is what? P2 minus P naught minus P2. Like this you can do. Okay, so this is the question you will get, and all the only thing. See, the concept is this only. Expression will be this also. 1 by T ln P naught by Pt. The only thing is what? Depending on the stoichiometric coefficient. Okay, depending on the stoichiometric coefficient, its expression will change, this pressure will change, and then this expression will change. So depending on the reaction, you can find out the various partial pressure, total pressure, and then the expression of K. Correct? Okay, now the same thing, one more case we'll discuss over here, that is volume related problem, because we know volume and concentration is also related to each other, right? And pressure and concentration also relate to each other, right? So pressure concept we have already done. Next, write down volume related method. How do we express the volume term, right? Volume related problem. Okay, now we know volume is directly proportional to what? The number of moles. Okay, so we can directly use the volume term into the expression of it. Okay, just you see, this is a bit like not that tricky, but you have to understand this like this. Okay, suppose you have this, so first of all you write down this volume is directly proportional to number of moles. Okay, at constant pressure and temperature. See, any reaction, if it is not mentioned, right, assume to be takes place at constant pressure and constant temperature. Correct? Okay, so now you see there are few reactions we have. All these things are possible when we have like no again gaseous reactant and product must be there. Then only this volume and pressure things will come into the mind. Okay, okay. Now you see if I write down one expression, one example I am taking down. Okay, just with this example we'll try to understand. Example we are taking, all these are first order kinetics we are assuming. Here also you write down first order, and in the previous one also you write down first order. All these expressions are first order. Mainly we'll deal with first order only. Suppose if I write down this reaction, 2N2O5 gives N2NO2, 4 mole of NO2 plus O2 gas. Okay, now if I assume the initial concentration or number of moles, suppose it is A naught, 0 0 number of moles. Okay, A naught number of moles here. After time t is equals to t, this becomes what? A naught minus what should I write? A naught minus
X,
2x.
X,
X also you can write. X also you can write. But whatever the coefficient you have here,
yeah,
that you take here, it will be easy, right? See, 2x here, so here it becomes 4x, and here it becomes x. Otherwise, if you take x, it becomes 2x, it becomes x by 2. Right. So to avoid that x by 2 expression, we are taking 2x over here. That is the only thing. You'll get the same answer into there also. Right. On long standing, when t is equals to infinity, this becomes 0. This becomes what? A naught gives 2 gives 4. 1 gives 1 by 2. So you'll get 2 a naught, correct? And this is a naught by 2.
yeah.
Right. For this reaction, if I write down the expression of k, what it will be? 1 by t ln of a naught by a naught minus 2x. See, we are taking the reference of this reaction. Again and again, I am repeating this thing. This expression, this term, because this will be same, right? This concentration term will be changed when the reaction will change, or stoichiometric coefficient you write down in different manner, right? So depending on the reaction, we are writing down this concentration term or pressure term over here, right? So you see, if V T is the volume of gas, suppose if I take like this, now we are coming back to this volume term here, right? And I assume what? After time t, Vt is the volume collected. Vt is the volume collected of the gas, right? And gas is what? Oxygen we have here. Volume of O2. Okay, volume of O2. So, so what we can write at time t is equals to t. What is the expression we have here? What we can write down the expression? And okay, infinity we have also, no? So at time t is equals to infinity, also write down here. V infinity is the volume here. Okay, volume of O2. This is the notation we are using. Okay. So what we can write here, that k is equals to k is equals to k is equals to 1 by t, correct?
Yes, sir.
ln of ln of what is the
Volume of
expression in instead of a naught? What we can write? Can you tell me? See, you have to consider on. See, one thing. Listen to me, all of you, very carefully. Since all these are for gases, so you don't have to worry with this NO2 and 2O5. You have to do only with this, because this is the only gaseous term over here. First thing is this. Okay. So a naught we have to convert this a naught in terms of volume. Yes or no? So what we can write after time t is equals to infinity, what is the volume of O2? A naught by 2. Like number of moles of O2, A naught by 2, right? And number of moles is directly proportional to volume. Yes or no?
yes,
Right? So we can write down the volume of O2 at infinity. Volume of O2 at infinity will be A naught by 2. Yes or no? And that will be equals to what? V infinity, which we have assumed here. Right? So A naught we can write down what? A naught is equals to 2 into V infinity. Right? So ln A naught is what? A naught is 2 V infinity divided by A naught is again 2 V infinity. And what is x? X is nothing but Vt. So we'll write what? 2x we have here. So we'll write 2Vt. So expression becomes what? K is equals to 1 by T ln of V infinity by V infinity minus Vt. This is the expression we get.
This is at t is equal to infinity.
What?
So this is at t is equal to infinity.
Um, no, it is at any point of time. The expression is
So we're just
valid.
expressing it in terms of t.
Huh?
We're just expressing it in terms of
In terms of infinity, yeah, because in terms of v infinity only we can replace this. What we have done, we have only replaced this a naught in terms of volume. That is it, and that is coming out to be 2 v naught. That's why we are getting v infinity from over here. But this expression is true at any point of time. Sorry, at any point of time, right? And all you they must have given in the question. Okay, you don't have to worry with that. The only thing is what happens because of this stoichiometry coefficient, you'll get different expression here and then different expression here. If you are able to write down this expression correctly, all the information will be given. After this only you have to substitute and get the answer. That is what you have to do. Yes, Ramcharan. Okay, so now one note you write down into this. One note you write down. We use volume expression when the gases is only on the product side. Okay, on the product side, if we have gases only, then only we'll use this volume expression. We use, write down, we use volume expression when the gases is only on the product is only on the product side. Okay, then only we use this. Okay, now some reactions you just write down, like in which we can use this uh, volume expression. Some reactions are, the first one I have already given, 2O5 reaction. Okay, the another reaction you write down, NH4 NH4NO2 solid gives N2 gas plus 2H2O liquid. In this question again we'll use volume expression because the gas is only on the product side. Okay, disonium chloride C6H5 N2Cl. Okay, solid. This also gives C6H5Cl solid plus N2 gas. In this also we use volume expression, 2H2O2 2H2O2 aqueous. This also gives 2H2O liquid plus O2 gas. Okay, so whenever we have gaseous product, one of the gaseous product present, then we use what? We use volume expression. Okay, and with the data given in the question also, you will understand that the gaseous like volume expression you have to use. Okay, now you tell me one thing. We have finished one kind of question in which the data is given A naught, B naught, and rate. According to the rate, we'll find out the order of the reaction with respect to any reactant. Huh? One question we have finished now, in which A naught is given 2, 3, 4 data, experimental data. We have done. Okay, 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 okay. Now you see the another order of reaction, the another type of reaction that we have, which is second order reaction. Okay, just you give me one time. Second order reaction you write down. Second order reaction. See, this chapter is mainly based on first order reaction only. Okay, that is the only important thing we have. But second order we'll also see. Rarely you'll get some of the questions are there given, but it is not that much important. Okay. Now in second order reaction, we have two, three possibilities, right? One possibility is what? If you have only one reactant, I'll just write down. Don't write down this. Okay. If you have only one reactant, A gives product. Okay. And with respect to this only, the order of the reaction is two. Is it possible? Right? So one kind of possibility is what? When we have only one reactant present and the order of the reaction with respect to one reactant only is two. Is it possible, right? Another possibility is what? We can have two reactant, A plus B, which gives some product, and the order of the reaction with respect to both the reactant is 1 and 1. It is also again possible, right? Now in this also we have two possibilities. Like if we have two reactants, then initial concentration of both may be same or it may be different also. Correct? So we are going to discuss these possibilities, these three possibilities. Correct? One possibility is what? When there is only one reactant and the order of the reaction with respect to one reactant only is 2. Another one is what? When we have two reactant present and the order of the reaction with respect to both the reactant is 1 and 1. Okay. And in this cases, we can have initial concentration same, we can have initial concentration different also. Right. We can have other possibilities also. If you see, we are not going to discuss this because it is not there in our syllabus. We can have three reactant also with respect to this. Suppose it is -1, this is 1, suppose this is +1 and this is 2. This is also possible, right? The total order is what? 2 plus 1 minus 1, that is 2 only, right? We can have also one possibility is this is 0, 1 and 1. This is also possible, right? So like this we can have many possibilities. So all those things are not important. Only we are going to discuss the first three possibilities that I told you. Correct? Okay. Now you see the first case in this. Oh, sorry. Let it be. The first case in second order reaction. Case 1. That is, suppose we have only one reactant. A gives product P. Okay. A gives product P. Now, can you write down the expression for this? First of all, for second order reaction, I'll give you some example. Okay, later on, just you ask me. Okay. Some examples you must have to keep in mind. Now suppose if I have this reaction, then what is the rate of this reaction we can write? Can I write down this? Tell me yes or no. Minus dA by dt,
So you
right?
asked us to get this
Huh?
as of-
We have derived second order.
no, sir, we have to do it as homework.
Second order we have derived or not?
No, sir, we have
Okay. So this is equals to what we can write? K
to
A 2. Yes or no?
yes.
Now this one you have to solve. D concentration of A by concentration of A square is equals to minus K dt. 0 when the concentration is, when the time is 0, concentration is, suppose we have A naught, and when the time is t, concentration is, suppose we have AT here. Correct? Can you solve this integration? Siddhant, are you getting all these?
Yes, sir.
Okay. Only thing, Siddhant, see what we are doing. This is the rate expression with respect to A we have is equals to K into concentration of A square. Why this square we have? Because the order of the reaction is 2. If it is 1, we'll write 1 over here and then we can derive this again. Okay. So when you derive this, you'll get this expression. Okay, I want you all to derive this. Okay, don't write down the expression directly. Okay, it is important for you. Once you derive this, it will be easy. You feel it is easy. Otherwise, you have to memorize the formula. 1 by t into what we get?
AT minus A naught by
1 by at minus 1 by a naught, right? This is the expression of k and t in second order equation, right? Can you tell me the expression for t half?
1 by K.
At t is equals to t half, what is the expression we have? At is equals to a naught by 2, right? These two, t and at, we can substitute into this, and that will get t half is equals to 1 by k into a naught.
Yes, sir.
This is what we get. Okay, now few graphs we'll see into this. Copy down all these first. Done? All of you have written? Okay. Now you have to draw certain graphs into it. First graph we have, that is rate and concentration graph. This is rate and concentration graph. Okay. Then we have rate and concentration of reactant and time graph. It is the concentration of reactant and time graph. Next one, 1 by concentration of reactant, RC, concentration of reactant and time graph. You write down properly all this. Here we have 1 by concentration of reactant. Okay. T half here we have T half, and this side we have 1 by A naught, initial concentration. 1 by A naught, initial concentration. One more, if I write down, suppose here we have rate and concentration square. Concentration means concentration of reactant. Okay, tell me, what is the first graph we get? See how this rate and concentration related. R is equals to K concentration of A square, right? So this graph is what? This graph is like this. Parabola,
Yeah,
correct?
yes.
Ramcharan.
Yes, sir.
Okay. Who all are there from Kormangla?
For only me.
Only you are there, no? So you, Ramcharan, and Siddhant. Only three people are there.
Yes, sir.
Okay. Okay. Now this R and concentration is square from this relation only. What we'll write? It is a what?
N.
Straight line passing through origin. And this slope is what? Slope of this is the rate constant K. Correct? Concentration of reactant and time graph. With time, the concentration of reactant is decreasing. Suppose initial concentration we have here. So with time, the concentration of reactant is decreasing. It goes like this, and it will never touch this axis because the concentration is never zero, because the 100% reaction never completes. Okay, and this is what? This is non-exponential graph here, right? This is non-exponential graph. What is 1 by concentration of reactant and time graph? Is it a straight line like this? Tell me.
Yes.
And what is this point? 1 by A naught. This distance is 1 by A naught. The expression that we have done just now, from this you can understand Siddhant, are you getting all these? Okay. T half and concentration 1 by concentration graph is what? It is again passing through origin, right? T half is equals to 1 by K not. If I ask you this graph, then what you'll do? T half and A naught, which they won't ask. But what is this?
So inversely proportional. So there'll be a yes, there'll be a curve like there'll be asymptotic to both paths.
It goes like this. Like this it goes, right? So this kind of graph you can draw easily. Okay. So there are a few graphs we have which is important for JE point of view. Some example of second order reaction you write down. Some example you write down. 2O3 gives 3O2. Second order reaction. 2NO2 gives 2NO plus O2. This is also second order reaction. Right? Okay. Now to generalize this, we are going to derive one expression for nth order reaction. All of you have done this, no?
Yes.
Okay. Now you see, to generalize all this expression, we are going to derive the nth order reaction. So write down nth order reaction. Oh, sorry, we forgot, no? We have to do that for second case also, no? First we do the second case. Case 2. What is the case 2? When we have more than two reactant, sorry, more than one reactant, write down case 2. If the number of reactant is 2, if the number of reactant is 2 and the order with respect to each reactant is 1, order with respect to each reactant is 1, right? So what we can write, you see, suppose we have A plus B and it gives product. Initial concentration, first we are assuming equal 0. After this it becomes what? A naught minus x, and this is A naught minus x is equals to x. Correct? So we can write what? Again, rate is equals to what we can write? Rate is equals to minus d concentration of A by dt is equals to what we can write? Minus d concentration of B by dt. This also we can write. Yes. And this both will be equal to dx by dt. And that will be equals to k concentration of A to the power 1 concentration of B to the power 1. Is it clear?
Yes.
Because order of reaction with respect to both reactant is 1 only. Huh. Ha. Then we'll have different thing. If suppose we have like this, A plus 2B gives product, correct? Then we have A naught, it will be A naught minus x. 1 reacts with 2. So A naught minus what will write? X reacts with 2x. And this gives you what? X only. Right? What? What will not change? Rate. So no, obviously that will change. See, rate expression will change here. You will understand. Just bear with me 2 more minutes. Okay, you'll understand how it change. You see, now when you write down this expression, okay, Ramcharan, now dx by dt is equals to what we can write? A k into a minus x, sorry, a naught minus x into a naught minus x. Yes or no? Siddhant, are you getting all these? Because the this is what? This is the concentration of A and B at time t, correct? So at time t, the concentration of A is A naught minus x. Concentration of B is A naught minus x. So we can substitute these two over here. Now you see the expression becomes what? Dx by dt right, is equals to K into A naught minus X square. Now you can solve this, no, integration.
Yes.
Dx by A naught minus X square is equals to K dt, right? So what you'll get when you solve this? You'll get same expression that you get over there. What we got there, K is equals to, I'll write down.
1 by t, 1 by a naught minus 1 by t.
So we got this. K is equals to 1 by T into 1 by
1 by
AT,
t
1 by AT minus 1 by A naught. If you take LCM of it, you'll get what? 1 by T into A naught minus AT. What is AT? A naught minus X. In the numerator, we'll get this divided by A naught into A naught minus X. Correct. And that will be what? K is equals to 1 by T into X by A naught into A naught minus X. In this form, also we can write down the same expression, right? Same expression you'll get here also. Because when you integrate this at point time 0, what is the value? Because you see here, understand this. Limit when you substitute, because it is dx, no? So what is the value of x at time t is equals to 0? 0. So here it is 0. At time t is equals to t, what is the value of x? It is x only. Correct. Now you can solve this easily. X to the power minus n plus 1 divided by minus n plus 1, and then you'll get the integration, so you'll get the expression over there, which you'll get same expression. This expression only you'll get. You can solve, you'll get this. Just you solve this integration fast, Ramcharan, Siddhant, both of you. Did you get the same expression? Yeah. So now you see here, Siddhant, Ramcharan, your question. If you get this a plus 2b, right, then you get a naught minus 2x. Then this solution of this expression becomes difficult. Why it is difficult? Because if I can make changes into this only, you see a naught minus x into a naught minus 2x we'll have to write over here. Then integration will be difficult. So since it is chemistry, so you will not get those expressions in which you have to integrate. You have to use some concept of integration, some vast concept of integration. Correct. So you will not get those kind of all. But yes, if you get, then you have to use your concept of integration, solve this integration thing, then whole expression will be changed. You will not get the same expression at that as you are getting over here. Understand my point? Okay, so basic thing is what? Write down the expression according to the stoichiometric coefficient. Write down the concentration left after time t or whatever initial it is. Then rate expression you write down and then you integrate this. This is what you have to do in all the type of reactions. Okay, if the reaction is not simple, and when I say simple, it means stoichiometric coefficient is 1, right? So when the stoichiometric coefficient is not 1, then your integral part will be where we have to integrate this. That will be a bit difficult. Okay, and accordingly you have to do. Understand my point? Okay. Now the second case only, if you take, you tell me one thing. If you take here, we'll do this also, but I am making some change into this only to make you understand. Siddhant, have you done this? Yeah. Okay, then copy it down fast. Let me know once you are done. Okay, so now you see the second case we are considering here. If the concentration is not same, right? Order is 1 with respect to both the reactant, but concentration is not same. Here suppose we have B naught. Then here also what we'll write? B naught. Here what we get? B naught. So the expression here will get what? So you just copy down case 2, you write down when the initial concentration of both reactant is different. This you write down case 2. Case 2 and the second thing into that. When the initial concentration is different, then till here, from this reaction to this expression, till here, you just copy down, then we'll solve this. How do we solve this expression? Done?
Yes, sir.
Okay. Till here you have copied, no? Siddhant, Ramcharan, till here?
Yes, sir.
Yeah.
Yes, sir.
Yeah. Now you see. How do we solve this? So basically, you can do this in a better way. Like, it is the integration only, right? So we have this expression dx by dt is equals to k a naught minus x into b naught minus x. This is what you have to solve. Correct.
Yes.
Now you see one thing, a naught minus x into b naught minus x. We can also write this as 1 by b naught minus a naught into 1 by a naught minus x minus 1 by b naught minus x. Can we write down this?
The 1 by the left hand side should be 1 by
Huh? Left hand
left
side.
hand side 1 by a naught minus 1 by a naught.
Correct. 1 by a naught. Yeah, it's correct. Here we'll write 1 by a naught minus x by b naught minus x, right? Okay. So now this we can write what? 1 by a naught minus x into b minus x dx is equals to k dt, right? Okay. So 1 by a naught minus x and v naught minus, and we can substitute this. Our calculation will be easy. So 1 by b naught minus a naught, I take common. Here we have 1 by a naught minus x minus 1 by b naught minus x dx is equals to k dt. Now you integrate this from 0 to, oh sorry, okay. So from 0 to, at time t is equals to 0, x is what? 0. At time t is equals to t, what is x? X only. So now when you integrate this, you solve this integration. Okay, I'll just give you the expression here that we get.
By t
Ln of
b naught minus x by
into something also will get.
ln of
We'll get this expression, you see. K is equals to 1 by t into b naught minus a naught, right? Ln a naught b naught minus x divided by b naught into a naught minus x. We'll get this. Check your calculation.
oh yeah. Oh yeah. Once you apply limit.
Ramcharan, done?
Yes, sir.
So once you are able to write down the rate law expression, after that it is nothing to do, right? There is very less thing. Everywhere we are doing the same thing. Okay. So these are the two possible cases in second order reaction, when we have only one reactant and when we have two reactant. Two reactant, again two possible cases. Both initial concentration are same for both the reactant, and initial concentration are different when both the reactant. So you'll get this expression. Okay, and I'll just ask you to memorize this expression. Okay, this one is, so it is a bit easy, right? But once you are going to derive this expression in the exam, it's very difficult for you to do, because you don't have a space over there. No, you don't have much space. Okay, so if you practice more and more questions, these expressions you can you will memorize on your own. Okay, you don't have to put effort into this. Okay, now coming back to this, if you have nth order, the last expression for this we are doing for nth order reaction, how do we derive the general expression? This nth order, n can be anything, 0 1 2, whatever we have discussed just now till now, right? Nth order reaction. So for nth order reaction, suppose the reaction we have, A gives product. Can you tell me the rate expression? What should we write?
K, sorry, rate is equal to K times concentration of A to the power n.
A to the power n, and left hand side what we have? D, concentration of A by dt, right?
The-
And that too minus sign we have here is equals to K, concentration of A to the power n. All of you are comfortable with this expression, no?
Yes.
Yes, sir.
Okay, Siddhant.
Yes, sir.
Okay, so now what we have to do next? We have to integrate again, and it's simple integration. Minus D concentration of A by concentration of A to the power n is equals to k dt, right? Now if you have to integrate this, so what is the limit we should put? Limit when t is equals to 0. What is the limit we have here? A naught. Suppose at time t is equals to t, what is the limit we have here? At. Solve this. What you are getting, you tell me, or I'll write down the expression here.
Yeah. That's very simple.
Did you get this?
Yeah. So concentration of, oh sorry, sorry.
At to the power 1 minus n, right?
Yeah, A to the power 1 minus n minus A naught to the power 1 minus n divided by n minus.
Divided by n, so I'll write down n minus 1 here only. Divided by n minus 1 into is equals to kt. This is what the expression we have, right? Or in the same way, if you want to write, then you can write down k is equals to 1 by t into this, right? This is what the expression we are using till now, right? Now you see, when n is equals to 1, then what we have? This term becomes what? 0, infinity, right? Undefined.
Mm-hmm.
Undefined. So this expression is not valid for first order reaction. So n must not be equals to 1. Correct? Now tell me the expression of T half for this reaction. At T half, T is equals to T half, AT is equals to A naught by 2, right? So when A naught by 2, if you substitute here, what you will get, you see, K is equals to, or T half is equals to 1 by K, right? And n, suppose I write down here only, n minus 1. Open bracket, AT is what? A naught by 2 to the power 1 minus n minus A naught to the power 1 minus n, right? A naught to the power 1 minus n I can take common. So that becomes what? A naught to the power 1 minus n divided by k into n minus 1 into what we can write? 1 by, or 2 to the power n minus 1 minus 1. Can I write down this?
Yes.
So you see here, T half. is directly proportional to what? A naught to the power 1 minus n. 1 minus n, right? And that is what we were getting over there. Okay. When n is equals to 1, right? Which is not true because n cannot be 1 according to this expression. But T half expression we are getting correct over here. N is equals to 1. T half is independent of initial concentration that we get over there. 0.693 by K. If you remember, T half of first order, right? What is the expression for T half of zero order?
Uh,
A naught by 2K. So when n is equals to 0, you put over here. T half is directly proportional to A naught, which is true over there also, right? When you put n is equals to 2, T half is inversely proportional to initial concentration, which we have done just now, right? So this we can cross verify also. All these like term that we have got is correct from here, right? So these are the few order of reaction that we have done. Okay, and everything is same, right? There is no difference we have here into this. Okay, only thing is what, when order is changing, rate expression you have to write down in a different manner, and then you have to find out the answer. Correct. Now, on the basis of all these expression, you will have question given in the module that you can solve now. Okay, various time, what is the concentration, you have to find out. There are many questions given, any book or any module you can go through. Okay, so we are like moving ahead into this. Next, you write down the reaction. Okay, how reaction takes place, what is the mechanism behind the reaction. Okay, so first you write down the thing into this: collision theory, collision theory of reaction. Okay, collision theory of reaction. See, what is collision theory? It says that when any reaction takes place, okay, suppose if I write down, you don't write anything now, okay, A2 plus B2, okay, it gives suppose 2AB. Then this reaction is about to occur, okay, and for this you must have some criteria. Okay, you must have some criteria. And what is that criteria? See, if you like recall, we have done the law of mass action, right? Law of mass action we have done, and law of mass action, oh sorry, in law of mass action we have used a term over there, that is active mass. Yes or no?
yes.
Active mass, one term we have used over there. And what I say, that active mass is nothing but concentration, you assume that as a concentration only, right? Now active mass is what, you see, if you have this reactant, right, and this reactant, if this reaction has to, takes place, has to occur, then the collision between the reaction molecule has to takes place, right? The reactant molecule must collide with each other. Okay, and when they collide, if the collision is effective, right, effective collision, when I say, listen to me very carefully. Okay, effective collision, when I say, it means the collision is sufficient enough to convert reactant into product. It is not necessary that all collision are effective. Did you get this? Right? And for any collision to be effective, every collision has to overcome two barrier. And that barrier is, don't write anything now, just you listen to me. Orientation barrier, orientation barrier, and energy barrier. If any of these barrier is not overcome, okay, has not been overcome, then we cannot say that okay, the product forms in the reaction. We are not sure with that, maybe, may not be correct. But if both the barrier is getting overcome, right, then the reactant will convert into product. Okay, so every collision or every reaction has to overcome these two barriers, then only the reaction proceeds. Okay, now coming back to first thing, what is this orientation barrier? Okay, now suppose two molecules, if you have, okay, this molecule or this two molecule collides like this also, head on collision takes place. One possibility is this with one orientation. Another possibility is this, what one molecule is this and other molecule is coming in this direction, right? Another possibility is what one molecule is here and another molecule is coming like this, it is going like this, right? Suppose one molecule is going like this and another molecule is going like this, then also collision takes place, but the direction is different, you see, right? This molecule is going over here, this molecule coming over here, so here also collision possible, again direction is different. So point here it is what, like I said, active mass, right? So if you have reactant molecule here and reactant molecule here, on the surface of the reactant molecule, all these surface area are not active, right? We have few area into this, like some part of it is, we call it as active surface area, right? Some part of it is active surface area, and the mass of this active surface area, we call it as active masses, correct? So when the collision takes place in such a way that this active surface area comes, takes part into the collision. Understood my point?
There's a surface area of the molecule.
Yeah, on the surface of the reactant molecule. See, when we have the reactant molecule, no, right? So it's like volcano. Volcano, have you must not have seen, but there is a mouth of the volcano from where the lava comes out, right? It is not from every point, it won't come out, no. So this point is what? This point is very prone for this eruption of this volcano, correct? So one point is very prone over there, whatever the surface of Earth we have, right? Similarly, what happened? All these are surface of Earth only, correct? But it's not like every point of time the lava, every point the lava is coming out. Eruption takes place from one significant point. Okay, wherever it finds easy, the lava comes out from there, right? So similarly, what happens? The reactant molecule that you have, okay, reactant molecule also, whatever the surface area of the reactant molecule, we have only few part of the surface area only which is active for any reaction to take place, right? It means when those part comes into the collision or takes part into the collision, then maybe the reaction takes place. Understood? If suppose this part and this part is colliding, which are not active surface area, then the reaction won't take place. I can't say that it won't take place. The chances are very less. Okay. So the point is, for this active surface area to take part in the collision, the reactant molecule must have some fixed orientation. Yes or no? Orientation means what? In which direction the reactant molecule is coming towards each other so that the collision takes place. Okay, so this we call it as orientation barrier. Understood? Similarly, we have energy barrier also. Energy barrier means what? The reactant molecule must have some minimum amount of energy so that it forms an activated complex, which is the intermediate, and then it converts into product. Okay, what is the energy barrier? We'll come to that later on also in this section. Okay, after orientation thing. But to one thing you must keep in mind. Okay, when both condition are satisfied, orientation plus energy, then reaction takes place 100%, right? If one of these is not one of these conditions is not satisfying, okay, then a reaction may not be possible. We are not sure about that. Okay, both possibilities are there. Okay, so write down into this the first thing, collision theory of reaction. Did you get this? Um, what is your name, Ramcharan?
Yes, sir.
Okay, so write down this point, you write down, chemical reaction takes place because of the collision among the reactant molecules, because of the,
You taking some.
are you getting me now? Hello, Siddhant?
Yeah,
Yeah,
yes, sir.
yeah, write
Yes,
down. You understood, no, whatever I said?
yes, sir.
Okay. Write down, chemical reactions takes place because of the collision among the reactant molecules Next line you write down collision frequency, which we denoted by Z. Okay, collision frequency. Definition of this you write down. Collision frequency Z. Write down. It is the number of collision takes place. It is the number of collision takes place per second per second per unit volume of the reaction mixture. Number of collision takes place per second per unit volume of the reaction mixture. Next line you write down all collisions. Yeah,
Of the reaction.
reaction mixture. Yeah. Next line you write down all collision does not bring all collision does not bring a chemical change. Chemical change means what? Conversion of reactant into product. Okay. All collision does not bring a chemical change. Collision which produces a chemical change. Collision which produces a chemical change are called effective collision. Are called effective collision. Non-effective collision. Non-effective collision are those which does not produce a chemical change. Which does not produce a chemical change. Okay. Next line. There are two barriers. There are two barriers which are need to be cleared. There are two barriers which are need to be cleared for any collision to be effective. For any collision to be effective. Okay. First one you write down orientation barrier. Orientation barrier. Write down into this. The reacting molecule must collide. The reacting molecule must collide in proper orientation for effective collision. Proper orientation for effective collision. Okay. You see this? Suppose we have A, and this collides with B. This forms an intermediate first, which is this AA bond is about to break, AB bond is about to form, and this BB bond is about to break. If all conditions are satisfied, then this converts into AB and AB. Sorry. This converts into AB and AB. This is the product we get here. Okay. So if I write down in this diagram form, this is the two molecule we have, and this is the another two molecule we have. Okay. And these two are about to collide with this with proper orientation, suppose. Then this two forms like this, This is the intermediate product we have. This one is this, and then it again dissociates, which is not looking good. Okay, but you can understand this is the product we get here. These are the molecules basically. Okay, different size molecules I'm representing in this way. Okay, but in the same way, suppose if you have molecule like this and it is colliding in some different orientation, then maybe the product does not form. Okay, so this we call it as orientation barrier. Okay, on this particular topic, energy and orientation, you may have some assertion reason questions. Okay, true false kind of question. Okay, numerical questions are not possible into this. Okay, now you see next energy barrier. The second barrier we have. Okay, write down. In this first thing you write down threshold energy definition. These definitions are also important from board point of view also. Threshold energy. Write down. It is the minimum amount of energy. It is the minimum amount of energy which colliding molecule. It is the minimum amount of energy which colliding molecule must have to make a chemical reaction possible. To make a chemical reaction possible. Okay, it is fixed for a reaction. It is fixed for a reaction. Next line. A collision between high energy molecules. A collision between high energy molecules forms forms an unstable molecular cluster. Forms an unstable molecular cluster called activated complex. The lifespan called activated complex. The lifespan of these activated complex is very small and further it breaks down and further it breaks down into new substance called product. New substance called product. Done.
Yes, sir.
Next line. The energy associated with the activated complex is known as activation energy. In bracket, you write down activation energy. In bracket, you write down like this EA, activation energy.
The energy associated with
Activated complex.
is known as
Activation energy. EA is the activation energy. Okay. Now you see one graph here. Okay, this axis you write down, y-axis write down fraction of molecule. On the y-axis you write down fraction of molecules. X-axis you write down energy. This is the energy axis we have. Okay, threshold energy is the minimum amount of energy, right? So all these molecules have different energy, you see, right? And all those molecules which has minimum of this energy, which is the threshold energy we have here, these molecules may bring the effective collision. Possibility are there, providing what orientation, one of the condition that we have, right? Providing the proper orientation. So this energy value is the threshold energy, correct? Threshold energy. And all molecules, all fraction of molecules which has more than or equal to this energy, threshold energy, may provide effective or may produce effective collision. One thing is clear, right? This energy, the peak that you have, this energy gives you here, it is the kinetic energy average kinetic energy of the molecules. Okay, and the difference of these two, average kinetic energy and the threshold energy, this difference, let me change the color at least. The difference of these two is the activation energy here. This is ea, activation energy, correct? So from this activation energy we can also write, so you write down the next one, and this one is important, this definition. Okay, sometimes they ask this thing in the multiple choice question. They'll give you the formula. What is activation energy? They'll ask you. Okay, activation energy. What we can write? See, from here to here, it is threshold energy, right? And from here to here, it is average kinetic energy, right? So activation energy is what?
Threshold energy.
Threshold minus average kinetic energy. Average K, yes or no? So this is one important definition you write down.
Yes, sir.
Okay. Now, two more graph we'll see over here. Now, one more thing. Okay, we'll see two more graph here. Two graph I am going to draw. So first, you let me draw that graph, and nothing you have to memorize here. Okay, I always say that in chemistry you have to memorize things. Okay, but here in this chapter there are very less thing that you have to memorize. You see, if I take this one as one of the axis, and this is the another graph I am taking. Okay, y-axis that you have is the energy. Okay, this y-axis we have is energy. Here also it is energy. And the x-axis we have progress of reaction as the reaction proceeds. Progress of reaction. And here also we have progress of reaction. Okay. Now, whatever the energy of reactant we have, okay, the energy of product may be more than the energy of reactant, maybe less than the energy of reactant, or maybe equal to the energy of reactant. All three possibilities we have, right?
Yes, sir.
Okay, so now you see, if I take this as the energy of reactant, okay, suppose the energy of reactant is this, right? This is the reactant, and the reaction goes like this, suppose, sorry, and the reaction suppose it goes like this. Okay, so this is reactant and this is product P. Similarly, we have here also energy of reactant is here, and the reaction goes like this. This is product and this is reactant. What is the difference in these two reactions? The energy of product is more in the second case, correct? Okay. So we are starting from this energy, and finally the energy of product is increasing, right? And here the energy of product is decreasing. This point is the activated complex. Activated complex, which is like an intermediate, this is also activated complex. Okay, this point. Now when the reaction starts from here, it goes till this activated complex forms. If here, if both condition are satisfied, that is orientation and energy barrier we have, if both conditions are satisfied, then an activated complex further breaks down into product. Otherwise it goes towards the reactant only. The reaction won't proceed further, correct? The same thing is true here also. If both conditions are satisfied, then the product form, otherwise it won't form. Right? Now this is the difference here. This is the energy of reactant, right? Whatever this energy we have from this point to this point, right? This difference is the activation energy EA, activation energy of forward reaction F. Write down all these things very clear and clear. Okay. So this is the, since reactant to product forward reaction, so this is the activation energy for forward reaction. Similarly, activation energy for backward reaction, if I ask you, this is the activation energy for backward. Is it clear, Ramcharan? Where are you? Okay, so is it clear? If the reaction has to go in backward direction, then this is the activation energy for backward reaction. What is this difference? It is the heat of the reaction or energy of the reaction. Del E or del H. Correct? So del E or del H, if you have to write down the formula of this, del E or del H, it is equals to the activation energy for forward reaction minus the activation energy for backward reaction. This is the formula we have. You mentioned this F is stands for forward, B stands for backward. Okay. Correct? Okay. So here you see, if I calculate this del H and del E for the first graph, is it negative or positive? Tell me. Amog.
So for the first graph,
First one, yeah. You have to
negative.
subtract this minus this. So obviously this value is more, no? You see this energy is more than this, right? So del H and del E is what? It is less than 0. And that's why it is what? It is the exothermic reaction. Is it clear?
Yes, negative.
Del H is negative for exothermic, no?
Yeah, yeah.
And that is why you see energy is starting, the reaction is starting from high energy and ended up with what? Low energy. So whatever the difference in energy we have, that must come out, no?
Yes.
And that is why it is exothermic. Is it clear, Ramcharan? And with graph also it is clear, and with mathematically also you see it is clear, right?
Yes.
Similarly, everything is same over here. Okay, this energy is what? This energy is what? Activation energy for forward reaction, EAF, right? And this energy is for activation energy for backward reaction, EAB. If you subtract forward minus backward, we are getting del H is what? Positive, right? And that is true also. It is endothermic. So this graph is for endothermic reaction and the first graph is for exothermic reaction. And you see, this mathematically we are getting, but you see, if the energy of reactant is here and we are going towards the higher energy level at the end of the reaction, so this difference in energy is more, right? So this extra energy must this reaction has consumed in this reaction to proceed, correct? That's why it is endothermic. So all these graphs are important. Okay. Now, one more thing you tell me. Okay, we'll discuss this later on. Okay. Just two fact we have here. Is it clear, Siddhant, Ramcharan?
Yes, sir.
Okay. So two facts you write down into this. Threshold energy is independent of temperature. It has nothing to do with temperature for a given reaction. Threshold energy is independent of temperature. Okay. Next line you write down. As temperature increases, as temperature increases, number of effective molecules increases, number of effective molecules increases, hence collision frequency increases, hence rate of the reaction increases. Correct?
So hence what, sir?
Hence collision frequency increases and hence rate of the reaction increases. We have done this thing in gaseous state also, if you remember. See, you can easily relate all these things since we are going towards the end of syllabus. Okay, so you can relate things. You see, if you increase the temperature, what happens? This graph will become what? A bit flat, like this it goes. Now you see more molecule is there in the with the threshold energy value, correct? So more molecules are there in this region, so more will be the collision, correct? More collision means what? Collision frequency is more. More collision frequency means what? High will be the rate of the reaction, correct? That is, and this graph we have discussed in that thing, gaseous state, right? Most probable speed, most probable RMS and average, right? We have done this over there. The same thing it is here also, right? Okay. Okay, now you see all these things that we have discussed, it is under concentration term. Like if you remember, we have discussed, we were discussing factors affecting the rate constant. Okay, factors affecting the rate of the reaction. There we have discussed the first thing, that is nature of reactant. Okay, and then we have started discussing um, concentration. In concentration only, like I said, that concentration, the rate of any reaction depends on concentration in a very complex manner, right? Because it depends, it depends on the order of the reaction also, correct? So on the basis of the order of the reaction, we have rate and concentration relation, right? So we have discussed various orders: zero, first, second, nth order. In that also we have discussed various terms, that is t half life and all those terms we have discussed, right? After that we have discussed theory by which the reaction is taking place, correct? Now the third factor which affects the rate of the reaction is catalyst. Okay, so write down the third factor. See, I have given you the like the brief introduction of this chapter, okay, like how we are going. Okay, so all these things that we are discussing, it is under concentration only, we have discussed till here. Now then, the next factor we are going to discuss is catalyst. Understood? No? Okay, so write down the heading catalyst. Okay, catalyst, you see, there are two types of catalyst we have. Write down the definition of this catalyst first. These are the substance, these are the substance which affect the rate of a reaction, which affects the rate of the reaction without taking part in the reaction, without taking part in the reaction. Okay, so catalyst won't take part in reaction, but it affects the change in reaction. Okay, if you have to form ammonia from nitrogen and hydrogen, right? If you use catalyst, then with in the small time we can get more amount of ammonia, right? it is not necessary that catalyst always increases the rate of reaction. It may decrease also. We have both kind of catalyst. Okay, so you write down into this catalyst. So definition you have written, no? Write down there are two types of catalyst next. The first one is positive catalyst. Positive catalyst. Write down. These are the catalyst these are the catalyst which decreases the activation energy. Sorry, you have written this. Wait. Hello. Have you written this?
No, sir.
Then write down. These are the substance which increases the rate of the reaction.
So
Which
you just said reasons.
uh
You said
no, just write down next definition. Write down positive catalyst. I'm giving you again it. Okay, positive catalyst. Write down the definition. These are the substance which increases the rate of the reaction, which increases the rate of the reaction by decreasing the activation energy. Okay, so positive catalyst basically it increases the rate of the reaction. Negative catalyst is just opposite of it. Okay, it decreases the rate of the reaction. Okay, so next the next one you write down the negative catalyst. It decreases the reaction rate. It decreases the reaction rate by increasing the activation energy of the reaction.
this is for negative catalyst.
Yeah, negative catalyst. Negative catalyst decreases the rate of reaction by increasing the activation energy. If nothing mentioned in the question paper, only catalyst is mentioned, then we'll understand positive catalyst only.
So by increasing the activation.
Decrease the rate of reaction by increasing the activation energy. Okay. See, if I draw the graph here, okay, this axis is the potential energy or energy you can write down, and it is the collision frequency or collision number. Collision number here also it is collision number, and this is the potential energy. Okay, if one graph, suppose we have a graph like this, we have a graph like this, suppose. Okay, and one more graph we have, suppose this. Okay, so with if I use positive catalyst in it, okay, so positive catalyst, this is the reactant and this is the product we have. It won't affect the initial and final state, right? So R and P, reactant and product. But since positive catalyst we have, so this will decrease the activation energy by some amount, and then the reaction proceeds. So this is what the decrease in activation energy. Yes or no? Initially the activation energy is this from here to here. Now since the positive catalyst we have, so activation energy decreases and product forms. If you have negative catalyst, then it increases the activation energy by some amount, and then the product forms into this reactant and product. This is the change in activation energy here. So this red graph, red that I have drawn, it is with catalyst. With catalyst. And this catalyst is what? It is negative. And this red graph is again with catalyst, and this is positive catalyst. So more will be the activation energy, less will be the rate of the reaction. Understood my point? See, if this energy is more, right? So it has to travel more distance, no? Like it has to travel more energy gap is there. So it time take to overcome this energy barrier is more, right? So rate of the reaction will be less. If this energy is less, then less time it can overcome this energy barrier. Okay. So what we can conclude here, activation energy increases, then rate of the reaction decreases. And if activation energy decreases, rate of the reaction increases. Correct?
Yeah.
Okay, next write down the next factor, that is temperature. This one is important, temperature one. Write down the dependency of temperature. In temperature you write down the dependency of rate constant on temperature, the dependency of rate constant on temperature rate constant on temperature can be given by Arrhenius equation. Can be given by we'll take break after this, okay? Yeah,
Given by
given by Arrhenius equation. Arrhenius equation is this. I'll write down the explaining. A R H E N I U S. Arrhenius equation. Okay, and this is given by K is equals to A e to the power minus EA by RT. This is Arrhenius equation we have. Okay. What is K here? Rate constant. K is the rate constant. This is very important. Okay. This many questions you will get from this particular expression. It is rate constant. A is the frequency factor. It is constant. Okay. It is constant only. EA is what? Energy. And T is the temperature. R is gas constant. Gas constant. Okay.
So A will be different for different elements.
For one reaction it is same. For another reaction it will be different. Correct. Right. Okay. Now if I assume at temperature T1, the rate constant is K1, and at temperature T2, the rate constant is K2, I am assuming. Okay. See, this K and T only variable we have. EA is also constant for a reaction. R is also constant. A is also constant, right? So if I use this particular data in this expression, we can write down what K1 is equals to A e to the power minus EA by RT1, right? Yes or no? Ln, if I take both sides, we'll get what? Ln A minus EA by RT1, right? Now we'll stop for a minute over here. We'll discuss the graph of this also. Sorry. ln k and 1 by t graph. Correct. Suppose this axis is ln k and this is 1 by t. How do we get this graph? Is it this y is equals to mx plus c? Oh, sorry. So is it why this is not going? I don't. This oh, it is like this now. Okay, this graph will be like this. It goes correct. Now in this you see this one is y. Ln k is y. What is m? M is this. Yes or no? Slope. C is this, and x is 1 by t. Correct? No. Okay. So, so the slope of this line is what? Minus EA by R. Minus EA by R. And this intercept is what? Ln A. We are doing this on Skype. We are connected on Skype only, no? Okay. Just give me a second. Okay. So the point here is what? The slope is ln A, right? A is the Arrhenius factor, we also call it as, or Arrhenius constant, we also call it as, frequency factor, we also call it as, slope is minus EA by R. Okay. So this graph and this expression is important. Okay. In general, if I write down ln K is equals to ln A minus EA by R 1 by T. Correct. Now you see, if you know the slope of this line, okay, then you can find out activation energy because R you already know, right? One more very important thing over here, right? Sometimes what happens, you will get confused, or I have given this question to the other classes also. They asked me, sir, what is the unit of R will take here? Whether it is 0.0821 or 8.314. Then what is this? This is energy, right? So for energy, what unit of R we should take? Energy must be in joule, right? Joule or calorie or whatever it is. So R value will take what? R value will take 8.31314. That is the unit in joule only, right? Unit of 8.314 joule per mole Kelvin. Okay. So here we use what? The value of R will use, mostly will use, is 8.314 joule per mole Kelvin. Correct? Right, this also you keep in mind. So when you know the slope of this line, you can find out EA easily. If you know this intercept, you know A also, right? And when you know A, we know EA, you can find out the rate constant of the reaction. Okay. And when you have the rate constant with unit, you know the order of the reaction also, right? Unit of K gives you the order of the reaction. Correct. So all these things are related. Okay, that's why I always say, particularly in this chapter, you don't have to memorize anything into this. If you know the concept, you can do any questions. Okay, now coming back to this. Okay, this expression we have seen. Now for another data, you can write down the same equation as ln k2 is equals to ln a minus ea by r t2. Yes or no? Right. This is equation 1. This is 2. Can we subtract 2 minus 1? And we get this ln k2 minus ln K1 is equals to what we can write? EA by R 1 by T2 minus 1 by T1. Yes or no?
So shouldn't it be the other way around? 1 by T1 minus 1 by T2.
2 minus 1 we have done, no?
Yeah.
ln K2 minus ln K1 minus we'll write here. Chalo, ठीक है. Okay. So we'll write what? ln K2 by ln K1 is equals to minus EA by R open bracket 1 by T2 minus 1 by T1. This is the relation of the rate constant and temperature. Very useful relation it is. You will have many questions on this in your module also. Must keep in mind. You will have some calculation in this particular question, particular type of question, but you have to do. Okay. Now the similar kind of expression you must have done in chemical equilibrium also, if you remember. Went off equation, right? Remember that? Went off equation, no? ln K2 by log K2 by K1 is equals to minus del H by 2.303 R into D2 by T1, which is the same thing here. If ln, if you convert into log, in the denominator will get what? 2.303. Yes or no? What we can write next, log of K2 by K1 is equals to what we can write? Minus EA by 2.303 R into 1 by T2 minus 1 by T1. This is what we write, no? And the same expression we have done in chemical equilibrium also. The only difference there is what? We write here del H, not EA. Yes or no?
Yes.
Now, what is the thing over here? Right? Whenever you write this K is equals to A e to the power minus del H by RT, right? Then this becomes equilibrium constant, not rate constant. Must remember this. Right? It means when you write del H over here, it is for reversible reaction. Okay? It is for reversible reaction. But when you write this EA by RT, it is for irreversible reaction. Right? Irreversible reaction. And for irreversible reaction, this K is what? K is rate constant, not equilibrium constant.
Oh,
Is it clear?
yeah.
Okay. So whenever you see over there EA, it means this K, because you see why I have discussed this here. In the exam, you will have the paper of chemistry. It is not like, okay, see, this is chemical kinetics question. See, this is equilibrium question. So if they have mentioned this, that it is from chemical kinetics, you must know, okay, this rate constant. Correct. But since you will not get this the question like this, you will have a chemistry question, right? So if they have written del H over here, it means this K is equilibrium constant, not rate constant, and the question is from chemical equilibrium, not chemical kinetics. Correct. But if they have given here EA, then this K1 and K2 are what? Are rate constant. Okay. This you must keep in mind. It is important. Okay. Don't uh, like forget all these things. Okay. So Siddhant, did you understand this?
Yes, sir.
Okay. So we have done like most of the chapters, most of the portions of this chapter. Okay. And for board point of view, okay, for JE we have one portion left in which we have derivation. Okay, one small concept we'll discuss now. We'll take break after that. Okay, and then we can do at least one of that particular concept. Okay, sequence reaction and parallel reaction we have to do more, right? So just one more thing you write down. All the factors we have discussed, if you remember, we have discussed nature of reactant, we have discussed concentration, we have discussed catalyst, and the last one is temperature. Okay. So all the factors which affects the rate of the reaction that we have discussed. More K value, more rate constant, more will be the rate. Correct? Less value of K, less will be the rate of the reaction. Okay. Correct. Now you write down the next point, that is molecularity. Okay, see this molecularity and order, they have asked this question many times into the previous exams. Okay, molecularity, order, NEET also, JE also they have asked. Okay, and board also they have asked the difference in molecularity and order. Theoretical only, there is not much thing into this. Just you write down molecularity. It is equal to the sum of the molecules. It is equal to the sum of the molecules of reactants involved in the reactants involved in the balanced stoichiometric equation. Balanced stoichiometric equation. Next line. It can also be defined as the number of reactant molecules involved in the rate determining step. Okay, what is order? Order is a experimental value, right? Experimental concept. Yes. Next line, write down molecularity is a theoretical concept. Okay. Okay, order can be 0, negative or positive, or fraction also, right? But next line write down molecularity cannot be 0, negative, fraction, infinite, or imaginary. Molecularity cannot be 0. No, molecularity cannot be fractional. Molecularity cannot be fractional. I'll give you the thing into that. Okay, cannot be 0, negative, fractional, infinite, imaginary. Next line, it cannot be more than 3 because 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 three molecules, three write down like this, because more than three molecules may not mutually collide with each other. More than three molecules may not mutually collide with each other. Okay, so difference of order and molecularity are important. Okay, it is given in any book. If you see, very common thing, you can understand. Okay, few reactions you see. If I write down this PCl5, on dissociation it gives PCl3 plus Cl2. This is only one molecule, right? It is unimolecular. Okay. If you write down 2HI, I have given you this like this one. 2HI gives H2 plus I2. It is two molecule we have here, so it is bimolecular. Okay, if you write down 2SO2 plus O2 gives 2SO3, it is trimolecular reaction. Trimolecular reaction. See, catalyst also we assume as a reactant only. Okay, because we put in the initial stage only. No, that's why it is. So these are very straightforward. Oh, sorry, these are very straightforward, right? Like you can see the stoichiometry and you can see. But you see, if I write down this reaction, H2O2 gives H2O plus half of O2, right? Sorry, H2O plus this half of O2 we don't have. We have here. Okay, I'll write down first the reaction. It is okay. So we have 2H2O2 gives H2O plus
2H2O plus
2H2O plus O2, right? 2H2O plus O2. This is the reaction we have. Okay. So if you see this reaction, the molecularity is what? 2 bimolecular. But this is not, again, it is not elementary reaction. This reaction takes place in two steps. Now you see this. H2O2 gives first H2O plus elementary oxygen. Siddhant, are you there?
Yes, sir.
Okay. H2O2, further, it reacts with this nascent oxygen and forms H2O plus O2. Okay. This reaction is slow reaction and this reaction is fast. And slow reaction we'll know what is slow reaction. It is the rate determining step. Okay, so molecularity and order we find out from here only. When you add these two reaction, the final reaction is what? You see this O and O gets cancelled. 2H2O2 gives 2H2O plus O2, which is this. But since this reaction is not elementary reaction, it takes place in two steps. This one is the slowest step, which involves only one molecule. So it is a unimolecular reaction. Understood?
So how do you find rate from this? Like the
Rate equation you can write. What is the order of this reaction? H2O2 and all. Right. See, for this you have to write down the rate expression first. Okay. Rate expression you should know. Okay. So rate expression will be what? R is equals to K concentration of H2O2, right, to the power the order of the reaction. Okay, and then you have to write down the, see, you need data from this, no, initial concentration and all. Then accordingly you will find out the rate. Order you should know, right?
they should give us
They will give you the order. Without order, see, order you don't worry. Okay, you just have to keep in mind how do we write down the rate expression with the given order. Okay, and then how do we solve that? Okay, that is what we were doing like till half an hour back. Okay, half an hour, 1 hour back. Okay, so this is what, with the given order you can write down this expression and then you integrate, you solve, you will get the answer. Okay, but order, since it is an experimental quantity, they'll give you the order in the reaction. If they haven't given the order, okay, if the order is not given, then somehow they'll give you the order, like they'll give you K value with unit. From there you can find out the order of the reaction. Okay, like this.
so otherwise you can take it like that. But
What?
otherwise you can take
No, you cannot calculate. If the order they haven't given you, or rate expression if they haven't given you, RLE. If they haven't given you RLE, then also you cannot find out rate law expression. RLE is what? If the expression is given like this, R is equals to suppose K, concentration of A and concentration of B, then what is the overall order? 1 plus 1, 2. If it is given, then we cannot write this on our own. Did you understand? No, this thing we have discussed already many times. Class. Okay. So if this is not given, you cannot find out. Okay. So this is it for this. No, the major portion we have covered. Okay. For board we have done everything, but for JE point of view, we have 2, 3 concepts, not concepts. We have derivation, and which is very very important because they ask questions from that. Okay, and in the exam you don't have time to derive that because the derivation is I won't say complex, but it is a big derivation. Okay, so it takes time also and it takes concentration also. An exam you cannot derive this. Okay, so that contains sequential reaction, parallel reaction, and reverse reaction. Okay, three different reactions: sequential, parallel, and reversible reaction. How do we find out concentration of any reactant on product in sequential, parallel, and reversible reaction at a given point of time? That we'll discuss after the break. Okay, so it is already 7 o'clock. Okay, so by what time we'll start? So 7:10 will start. Okay, and then we'll continue this class till 7:45. Okay, okay, 7:10 will start. 8 minutes break.
Yeah, hello, sir.
Yeah, hi.
Hi, sir.
He left, I guess. Siddhant, you there?
I don't think he's there.
Okay, anyways. Okay, so we'll discuss one a particular reaction today. Okay, this is the last thing we are discussing today. Okay, that is a sequence reaction.
So will you finish the chapter today?
We have two more things left into this, like half an hour, 45 minutes things are left. Okay, most of the thing we have discussed. Okay, it's almost 90% things are finished. Okay, only we have to see few formulas into this, because as I said, you cannot derive all these things in the exam. Okay, so we are going to derive certain formula. I can give you the formula directly also, but again, it is difficult for you to memorize like that. Okay, because derivation is important for you to understand. Okay, so sequential reaction means what? Suppose we have A reactant. Okay, it gives B and B gives C. This is a sequential reaction. Okay, now we have two different reaction we can assume here. Yes or no? A to B is the one reaction and B to C is the another reaction. So we have two different rate constant also, K1 and K2. Right. So suppose at time t is equals to 0, we have only A present. So we have initial concentration of A is A naught. This is B 0 and C is 0. At time t is equals to t, suppose the concentration of A becomes AT, concentration of B becomes BT, or B simply you can write, right? BT or B simply, whatever it is. Okay. So I'll just write down like this only. A, B, and C. Okay. Now the question is, we have to find out concentration of A, concentration of B, at any point of time, concentration of C we have to find out. We have to find out concentration of B max. Okay, and time at which concentration of B is maximum. Okay, all these 5 things we have to find out in this, and we'll get a general formula. Okay, you see here, if I discuss the graph of this reaction, okay, it is the progress of reaction with time. Okay, and this is the concentration. Obviously, concentration of A is continuously decreasing, right? The concentration of A decreases like this, and all these are first order. We are assuming whatever we'll do after this, all are first order. Okay, like parallel also first order parallel reaction, and reversible also first order. So this is what, this is the, I'll write down wait, this is the concentration, right? This is concentration, and this graph represents concentration of A, right? Concentration of C also, it increases continuously with time. Concentration of C, yes Ramcharan, right?
Yes, yes.
Concentration of B, what happens, it increases initially, goes to a maximum value and then decreases. Why it decreases? Sorry, it can be, see, one thing you must keep in mind, it cannot be more than this A naught, right? So this peak should be less than, okay, that you must, I'll just do that, wait, like this it may be. Okay, this is the B max we have. Why it is decreasing? Because you see, B is, this is the graph of B we have. Okay, sometimes they ask you this graph also, they'll give you this graph, 1 2 3 4 graph, which one of these reaction they'll give you, which one of these is the graph represents that. Okay, so since B is forming in first reaction, it is a product in first reaction, correct? So according to first reaction, its concentration increases with time, but at the same time simultaneously it starts converting into C also. So for the second reaction, it is reactant. Okay, so it goes to a maximum value and then start decreasing, correct? So this is what the graph we have. Okay, now we see, this is the graph, important one. Since it is first order, so rate of A, what we can write, is equal to d concentration of A by dt is equals to K into concentration of A. Why only A? Because it's the first order, right? And we can solve this and we get what, AT is equals to, we have done this already, so I'm not going to do this again. So that will be what, A T is equals to, we can write A naught e to the power minus K1T. This is K1, right? Sorry. Okay, so this is the concentration of A at time T. So first thing we have calculated, this AT we have calculated, or A we have calculated. AT and A are the same thing. Okay, don't get confused with it. Okay. Now, if I write down the concentration of B also here, or rate of sorry, rate of B, rate of B, that will be what, rate at which, if I write down suppose D concentration of B by dt, it means we are assuming this B as a product, correct? Because it is positive. Yeah, and that will be equals to what, rate at which B is forming, which is K1 into concentration of A minus rate at which B is disappearing, K2 into concentration of B. Yes.
Yes.
Now we have to solve this differential equation. Ramcharan, did you get this? Siddhant is there or not?
Yes, I got it.
Okay. So how can we solve this deconcentration of B by dt? See, if you are able to write this expression, after this you have only mathematics, nothing more. Okay. So plus dV by dt plus K2B is equals to K1A we can write. And A we have already calculated this, you see. That will be A naught e to the power minus K1T. You try to do this on your own, right? I am just, I am also doing over here, but you don't copy down it simply. Okay, you try to do it on your own. Or if not, just copy it down and then try to do it at home on your own again, right? So this is what. Now all these concentration we have to find out in terms of initial concentration because it is given, right? A naught is given, K1 is given, K2 is given. So if A naught, K1, K2 is there in the expression, so our like that is what we need, right? That is what we are seeking for, correct? So this B we do not know. This B we have to find, correct? And everything it is given, A naught we know, K1 we know, K2 we know, right? Now the only trick we have to use here, a trick for to solve this integration, and that is what our job is, right? To solve this integration, what we'll do, we'll just multiply both sides by e to the power k2t. Here I'm multiplying e to the power k2t, and here also I'm multiplying e to the power k2t. Yes, Ramcharan.
Oh, yeah.
Yes,
Now what is this? What is this?
E to the power K2T
Into b. Is it clear, Ramcharan? If we can write this expression as d by dt of e to the power k2t into concentration of b, right? U into v, you can apply the formula, you'll get this. Yes, I need to do this? No.
no, sir.
And this will be equals to k1 a naught e to the power, what we can write, k2 minus k1 into t. Now it is simple, you see. E to the power K2T concentration of B D of this is equals to, we can write what, K1 A naught e to the power K2 minus K1 into T dt, correct? Okay, so now we can integrate both sides. You copy down till here, then we'll do next.
Yes, sir.
Done? Done?
Yeah.
Okay. So now when we integrate both sides, what will we get on the left side? Tell me, I don't have. Okay, we have e to the power k2t concentration of B is equals to what we get this side,
K1 by K2 minus K1
K1 by K2 minus K1 A naught
into naught e to the power K2 minus K1
K2 minus K1 into T plus C, right? It is indefinite, no? We haven't put over there a limit, we did not put, right? This is indefinite, so C we have to substitute. So this C value you have to find out. And how do we find out C? What is the condition we should apply?
and T is equal to 0.
0, B is 0. That we can apply, right? So when T is equals to 0, concentration of B is what? 0. So when you apply this, what is the C value you will get? Tell me the C value. See, this term will be 0.
No, sorry.
This term will be 0.
K1 by
K1 by
K1 by K2 minus K1.
K1 by K1 minus K2 into A naught.
Yeah, K1 by K2.
Because Ramcharan, this will come this side, no?
Yes, I am.
This side is 0. So K1 by K1 minus. And this C we can substitute here. Right? So here we get what? E to the power K2T concentration of B is equals to K1 by K2 minus K1 concentration of A naught e to the power K2 minus K1 concentration of T plus K1 by K1 minus K2 concentration of A naught. See, you might be, you're getting some, like this kind of feeling that what expression we are getting, it is so big and complex. How do we memorize this? Correct. Might be this kind of vibe you are having now. But when you solve this, no, we have not finished this yet. Okay. When you solve this, you'll get a very beautiful expression that you can memorize very easily. Okay, and that's why we are doing, once you have done this on your own, the derivation, you can write down this thing in the exam. Okay, but if you simply go to the if you simply jump onto the final expression, it is difficult to memorize that. Okay, so now you see what we'll do. Let's divide both side by e to the power k to t. Correct. So first of all, I'll take this common. Okay, these this term and this term will take common. Okay, so you remember one thing, here we have k2 minus k1, and here we have k1 minus k2. Okay, so if I write down e to the power k2t left hand side, concentration of B as it is, and k1 by k2 minus k1, concentration of A naught we are taking common, and what we are left with then, e to the power k2 minus k1 into t minus 1. Is it clear? Correct. So when you divide both side by e to the power k2t, then this common expression will be same. It won't change, right? And to t e to the power k2t will take inside the bracket. So this k2t and k2t will get cancelled if you do this. Yes or no?
So it, oh, yes, sir. Get e power minus k1 t.
K1t minus e to the power minus k2t. That is it. This is what the expression of B we have. Okay, so e to the power minus, see whatever you have written here in the numerator, I'll write down the final expression here, and you do this derivation again or on your own once at home, right? Concentration of B is equals to whatever we are writing down here, K1 divided by K2 minus K1. This you have to memorize A naught. Okay, this into whatever you have written first in the numerator here, minus of that into T, minus the other rate constant into T. And what is K1? If you remember, this is K1 here. That also you keep in mind. If they change in the question, suppose K2 they'll put here, K1 they'll put here. Don't get confused. K1 is the rate constant of the first one. Okay, that also you have to keep in mind. So this is the like expression for B we have at any point of time. Now you see, if you do not know this particular formula, you have to do all these things in the exam, and you get this kind of question. It is not like we are doing some advanced thing and all. You get this kind of question in the exam. Okay, it is there in the module also. You can go through. Okay, so concentration of B we have find out. Now it is easy. Okay, you have done this. No, can I rub this off? Can I erase this? Ramcharan done, no?
Yes, sir.
Now you see, every like any time we can balance the mass of the reaction, right? From mass balance, what we can write, initial concentration A naught is equals to what? Concentration of A plus concentration of B plus concentration of C. Right? We can write down this. A concentration you know, and that is what? A naught e to the power minus k1t. B you have already done. C we have to find out. And B, formula of B, if you see, it is in terms of what? Can A naught only. So this A naught left hand side minus this term minus concentration of B will give you what? Concentration of C. So I'll write down the formula. You can do this, it's just two step. Okay. The formula you'll get here is concentration of A naught, open bracket, 1 minus e to the power minus k1t minus k1 by k2 minus k1, k2 minus k1, open bracket, e to the power, what we had, minus k1t minus e to the power minus k2t. This is what the expression for C at any point of time. and this you don't have to memorize, okay, because if you know B, we can easily do by this one. This is two step, okay, you don't require any no time into this. So if you don't memorize this, but B, expression of B you must memorize. That is very very important. And why it is important? Because they ask questions on B only most of the time, and if you know B, you can find out C from this mass balance, correct? Now coming back to the concentration of B, write down this expression, both of you. Done, Ramcharan?
Yes, sir.
Now coming back to the expression of B, we have to find out next maximum concentration of B, right? For B max, what condition we can apply? Tell me.
That should be
dB by dt is equals to 0. So the B expression that you have, differentiate that and put equals to 0. You'll get time over there. And that expression is also not complex. Just find out this. So we can write d by dt of concentration of B, d by dt of concentration of B. If you see this K1 by K2 minus K1, A naught is constant. So this we can put outside, minus K1 e to the power minus K1 t, correct? Plus K2 e to the power minus K2 t, correct? And this will be equals to 0, right? So this term you let it be this equals to this basically. You see how simple it is now. We'll get what? K1 e to the power K1 t is equals to minus K1 t, and K2 is e to the power minus K2 t. K2 by K1 is what?
e to the power k2 minus k1.
E to the power K2 minus K1 into t. Take ln both side, because time also we have to find out, no? Ln K2 by K1 is equals to what we can write? Divided by K2 minus K1 is equals to what? T. This is the time after which the concentration of B becomes what?
Maximum.
Maximum. Yes or no?
Yes.
Write down this
Yes.
thing here. The time after which the concentration of B becomes maximum. This one they ask. Okay, K2 by K1. Sorry, we have K1 here. This one also. Whatever formula we are doing for B, that you must remember. Whether it is time, B max, we are going to do after this at B itself. Now, how do we find out B max?
So substitute that.
Substitute that T into the B formula that you have. You do that.
So will you be able to simplify it for after?
Yeah, you'll get very simple expression. You want, then I can give you the expression directly.
Oh, no.
Just try to do this. I'll write down one step. Okay. Many things will get cancelled and you'll get simple expression that you can memorize easily. B max, if we have to find out, we'll write this expression will be as it is, K1 by K2 minus K1 A naught, open bracket, e to the power minus K1 ln K2 by K1 divided by K2 minus K1. All these are e to the power, okay? E to the power minus K2 ln K2 by K1 divided by K2 minus K1, right? I'll suggest you one thing here. See what you do. What is the coefficient of ln K2 by K1 here and here? Here we have K1 by K2 minus K1, right? So what you do, you just take this minus of K1 by K2 minus K1 to the power of this ln by the log property, correct?
Okay.
So what you'll get, e to the power ln something over there, right?
Right.
So that becomes what? This term only.
Hmm.
And the same term will get here, and then you try to solve this. Understand, Ramcharan?
Yes, sir.
Try to solve this. Write down neat and clean, otherwise you will get confused K1, K2. Okay. So properly you write down.
Okay, sir.
Done.
Yeah.
So you get this probably.
That was very symmetrical.
So that's the thing will get cancelled. A naught, and here we get K2 by K1 to the power minus K1 by K2 minus K1, correct?
Yes, sir.
Minus K2
K2
by K1 to the power minus K2 by K2 minus K1, correct? Now what you do, this term, we can write this as 1 by this whole term, no?
Yeah.
So 1 by this you write down, and then you take LCM of this term. So this term into this you write down here, then everything will get cancelled, you see. K1 by K2 minus K1 A naught, open bracket, K2 by K1 to the power minus of K1 by K2 minus K1 into, we can write K2 by K1 to the power K2 divided by K2 minus K1 minus 1, and this whole divided by K2 by K1 to the power K2 by K2 minus K1. Am I right? See this.
Yeah, yeah.
It is K1, K2 minus K1 here. Ramcharan, see this.
Yes, sir.
Okay. Now, since the base is same here, you see, the power we can add. So you see what you are getting in the power. K2 minus K1 we are getting, and denominator also we have K2 by K1. So when you add the power, we are getting K2 minus K1 divided by K2 minus K1. So that will get cancelled.
Hmm.
So we are left with this. Ramcharan, are you getting confused? Amog, you also.
Yeah, so it's a bit overwhelming.
Yeah. So like, so previous step, what exactly to do?
Which one? Which one? The next, this one only. I have seen. See, we have here minus. No. So we can write what 1 by this whole term. Minus n will not be there. 1 by this whole term we can write down, and this whole further multiply here minus 1 by this. LCM only we are taking.
Oh,
Correct. So this term
yeah.
I can write 1 by whole this, and then when you take LCM, this term and this term will multiply, and this will get in the denominator. Correct, Amog?
Yes.
Now, when you add the power over here, so we can write by here what K2 by K1 to the power K2 minus K1 divided by K2 minus K1 minus 1 divided by K2 by K1 to the power K2 by K2 minus K1. Is it right?
Yeah.
So this will get cancelled. This will get cancelled. And when you take this K1 again LCM in the numerator itself, so in the numerator what we can write? K2 minus K1 by K1. This K2 minus K1 and this K2 minus K1 will get cancelled. Ramcharan, yes.
Yes,
So this
okay.
and this and this also will get cancelled. Correct? So we are left with what? We are left with this only. So B max value is K2 by K1 to the power minus of K2 by K2 minus K1 into A naught. This is it, the expression of B max. Okay, so you can see there are some symmetry kind of expression we are getting. K2 we have in the numerator here. Here we have K2 in the numerator, so here also we have K2 in the numerator. This K2 you have written here in the numerator, so here K2 minus K1 you have to write down. Okay, and then A naught. So this you have to memorize. You see how complex. I won't say it is complex, but you have to be very concentrated while you are deriving this. And in the exam, you will definitely do something wrong into this when you are going to derive all these things. Okay. So like this is it. For the constant. So we have calculated what? We have calculated A. We have calculated B. We have calculated C. We have calculated B max. And after what time the concentration becomes maximum. So out of this 5, this B max is important and T max is also important. What time the B is become maximum? Both them is very important. Okay. So this is it like in this section. Okay. Similar kind of derivation we have for parallel reaction also. Okay. And then we'll do one reversible. Okay. So we'll do that in the next class. Okay. Today we are winding up here only. Okay. So the thing is, from center modules, exercise 2, section A, section B, all question you can solve now. Only those questions you can leave which are parallel. Parallel reaction means what? This kind of reaction you see. A gives B and A gives C. This kind of question you let it be. And all those questions which are related to the reversible reaction. These two questions, these two type of questions, you let it be. Okay, we'll discuss that in the next class. We required half an hour, 45 minutes more to finish the chapter. Okay, and then you can solve all those questions. Okay. Okay. Chalo, फिर ठीक है. Thank you.
Thank you, sir.
Thank you. Okay. Bye.